for setting up this very interesting workshop in such a very beautiful place. So I'm Augusto Roncaglia from the University of Buenos Aires. I'm part of the group on quantum foundations and information in Buenos Aires. Here is a picture of our building. We don't have any beach over there, but we have good wine and meat. So we have a theory part of the group, where we have two permanent researchers, Juan Pablo Paz and myself. And we are proud that since last year we also have an experimental part of the group, which is a laboratory of cold ions and atoms that is led by Christian Schmiegelow. So now they are trapping the first ions. So we hope to have very interesting experiments soon. Okay, so today I'm going to talk about how correlations can be used for perform different tasks in different thermodynamic transformations. Last week we heard some interesting talks about how correlation can be used to improve some work extraction schemes, or how can be used to distill work. So today I'm gonna focus on correlations that happen, correlations that are revealed when a system is in contact with a heat bath at the given temperature, and when this happens in the single shot regime. So this is the overview of my talk. First, I will talk about correlations and work in the standard approach, without or outside the single shot regime. Then I will move to talk about how can we manage this single shot regime using the thermodynamic as a resource theory. Then I will talk about some interesting examples of how correlations are useful for some interesting tasks. And at the end, I will talk about our work on the work cost of correlated systems in the single shot regime. So as I said, I will consider transformations that happen at the background temperature. So standard thermodynamics tells us that a transition happens if between two states happens if the free energy goes down. So this is the second law. And if these transformations may happen, so at the maximum work that we can extract from the transformation is given by the difference in free energy. And if the opposite transformation can also happen, we have to invest the same amount of work. So in this sense, we consider reversible transformation, but this is possible only when you consider many particles, because as we know, work is a random variable, and we have fluctuations. So if we consider many particles, we know that fluctuations goes down as 1 over square root of n. So it is okay to neglect such fluctuations in the regime of a large number of particles. So fluctuations become important when we consider just small number of particles, and this is what I'm going to talk today. However, if we consider if we are concerned with the mean value of work, we know that if we are in contact with a heat bath, we can extract an average work equal to the free energy, the difference in free energy. And this is the same work that we need in order to create, for instance, a phase state. So one can consider the creation of correlations in this setup by asking, well, which is the energy that one should spend in order to create a correlated state out of a thermal state. And it turns out that since the work is given by the difference in free energy, we have to spend some energy in order to create correlations in this state. In this sense, we can say that correlations are costly. but as I said before, this approach includes correlations, fluctuations. So if we want to take into account the effect of fluctuations, we can study this. That there is an approach that came like a few years ago, coming from single-shot information theory, where treats thermodynamics as a resource theory. So let me say the set of rules of the resource theory of thermodynamics. So if we consider here a system with a given Hamiltonian, which is out of a thermal state, we say that this is a resource of the theory. Then we have a thermal bath at a given temperature. These states are for free. Every thermal state with an arbitrary Hamiltonian is for free in the theory. Then the system and the bath can interact via a unitary operation, which is which is energy conserving. That is, the unitary commutes with the full Hamiltonian. So we are asking strict conservation of energy, and at the end we can throw the degrees of freedom of the bath away. So these are the set of rules that an external agent can follow in order to perform transformations in this framework. So we say that this is the most general transformation up to here, and this is what we call a thermal operation. So pictorially, we will depict this thermodynamic, the thermal operation in this way, where a given initial state is transformed out to a final state. And the next interesting question that one could ask is, which are the rules, or when we can say that a given initial state can be transformed to a final one. And this is given by the thermodynamization condition that I'm not going to go into the details, because I'm going to talk about some more general stuff. So in this framework, we can also consider an auxiliary system, which we call a catalyst, that has a given Hamiltonian, and it would be in some initial state that after the transformation, it could be given back in the same state without correlation with the system. So this is called the catalyst because this is a resource that is not consumed after the transformation. And so it can be reduced many, many times. So if we consider transformation with the use of a catalyst, the necessary and sufficient condition for a given transformation of this type for block diagonal state, I mean states that are diagonal in the energy eigenbasis, is given by the cis infinite set of inequalities, which are called the family of free energies. And these are inequalities for this free energy that can be written in terms of the Renyi divergence between the state and the thermal one. So this infinite set of inequalities also contains the second law as a particular case, which is when alpha is equal to 1. And in fact, one need not consider all the possible values of alpha, it is enough to consider semi-positive ones. Okay, so we have this set of rules, and the following question is, how can we include work in this setup? So if we are interested in deterministic work extraction, one way to include work is by considering a given two-level system which has a given gap. That is, if the initial state of the system before the thermal operation is in the ground state, and at the end the state comes to the excited one, we can say that deterministically after the transformation we have extracted an amount of work given by the gap. On the other hand, if the state starts in the excited state and after the transformation it ends up in the ground state, we say that that after the transformation we inverted a work given by this gap. So now we can ask which is the maximum amount of work that one could extract from a given state. And this can be studied by considering this transformation where an initial state, where the initial systems is the initial state plus a battery in the ground state, and after the process, we have a thermal state, and the battery is on the excited one. If we maximize over this value of work, what we have is the extractable work that can actually be written as a difference between free energies, which is the free energy for the zero. On the other hand, we can ask, well, which is the work that one should invest in the inverse transformation? I mean, we start with a thermal state and we want to invert some work in order to create a state. So this is the transformation. And if we want to analyze the work cost, we have to minimize over the value of work. And it turns out that, again, this work of formation can be written in terms of the difference in free energy. In this case, the order infinity. As you may realize, in general, the work of formation is smaller than the extractable work. So this, sorry? Huh? A larger, sorry. The work of formation is larger than the extractable work, so this means that the energy that one should invest in the creation is less than the energy that can be extracted in the reverse process. So there's fundamentally reversibility in this regime, in the single shot regime. And well, this is just how to obtain the work of formation and the extractable work. But let me say that the extractable work in the deterministic regime has to do with the rank of the state. So for full rank state, it's impossible to extract any deterministic work. But this sort of irreversibility is not only restricted for in deterministic work extraction, but it also appears when one bounds the fluctuations in work. So if we constrain the fluctuations of work, it turns out that there is also an irreversibility in the mean value of work that one should invest in the creation of a state and the extractable one. And there is also a trade-off between fluctuations and the advantage of considering of allowing fluctuations in the value of work. So, but sometimes we are not one is not interested in study deterministic work extraction, but to allow a given small probability of failure. So the idea is that one can define deterministic work extraction by given a probability near 1 of extracted work and a small probability of failure. So in this way, one can define the deterministic epsilon deterministic work extraction in this way by this modification of the free energies, and it is like by introducing this error, these fluctuations in the work extraction or work formation, by which one could recover standard reversible transformation. Because as we know, the free energies are additive, so if we apply the free energy over tensor product of systems, we cannot obtain this reversible state. So one should include some small error in the transformation in order to recover standard reversible result. I will come back to this issue at the end of the talk. Okay, so this is the framework where I'm really interested in. And now I will show you some interesting examples of how correlations are interesting in this regime. So I will talk about 3 different setups. The first one is when one considers correlated catalysis. The second one is one consider correlation between the system and catalysis. And the last one is our work on the work cost of correlation systems. So imagine the following situation. We have a system in a state rho, and we want to perform a transformation to a state sigma. But it happens that we cannot do it in the single shot regime, but we know that the free energy of this state, that the standard free energy, is smaller than this one. So we can perform the transformation when we allow arbitrarily large fluctuations, but in a single shot regime this is not possible. So one may ask, what happens if we, instead of considering that the catalyst is returned in the same state, we allow some correlations between these multipartite catalysts? Well, it turns out that in this case, for block diagonal states, there exists, for every epsilon, there exists an epsilon closed state such that this transformation is possible with correlated catalysis, provided the free energy is of the final state is smaller than the first one. So, of course, the dimension of the catalysis would be very big, depending on the epsilon that we choose. On the other hand, if we allow also some probability of failure in the work, there is a correlated catalysis that allows us to extract in the single shot the free energy difference. So this is an interesting example of how correlation in the catalysis allow us to perform tasks that are not possible in other way. The other example is this very interesting, it's an interesting one, where we have the same situation. We have a system that starts in, that is in rho, in some initial state, and we want to perform this transformation that is not possible in the single shot regime. But it turns out that if we allowed correlation between the final state and the catalysis, there is again a block diagonal state. There is a epsilon closed state for block diagonal state that allows to perform this transformation where the catalysis is returned back in the same state, in the same local state, but with correlation with the system, and the local density matrix of this correlated system is this epsilon closed state, and the catalysis returned in the same local state. So this is interesting because it gives a single shot interpretation to the free energy without going to the thermodynamic limit. And in fact, last year appeared also a very nice result by Jens Eisert and collaborators, where they showed that there is also a similar interpretation of the von Neumann entropy when you allowed correlation between the catalysis. So now we could ask, well, which is the work cost of creating correlated systems? So let us see this simple example. We have this situation where we want to create, by spending some work, we want to create the correlated system. So now for simplicity, let us look at the very symmetric case where the local state of each of the system is the same, and they have the same Hamiltonian. It is a two-level system. So in the single shot approach, we have to look at this transformation. That is, we start with the thermal state, we apply some work, and we end up with a correlated state. So if you look at this example, we have a correlated state whose local density matrix are this one. So we are in this situation. And if we compute which is the work cost or the work of formation of this state, it turns out that it's smaller than 2 times the work of formation of a single state. So with this example, we show that the work of formation of a correlated system is smaller than the work of formation of 2 uncorrelated systems. And this is really surprising. And we could ask, well, is this a generic case? Is it always that if by creating correlation, one can reduce the work of formation in the single shot regime? So in order to look at this problem, let us consider the following one, which is the work cost of creating this type of N-partite ensemble. So the ensemble is defined by giving the number of particles, the local state, and the Hamiltonian of the system. For simplicity, let us consider that all the states are the same, so this is our like creating n copies with the local density matrix rho. So we ask which is the minimum work cost. Standard thermodynamics tells us that, well, if you want to create this state, the best you can do is to create each copy one at a time. If you consider the single shot regime, as I told you, we have to consider also correlations. So in this case, there are many ensembles or many states, multipartite states, that are compatible with this prescription. And this is the condition of partial trace over each of the systems. So this is what we do. We want to find the Z work of formation, that is the work of formation of this correlated system. So in order to do that, we have to minimize the work of formation over all states that are compatible with the local trace condition. So we have a set of states that are compatible with the partial trace condition, and we want to find which is the multipartite state that attains the minimum work of formation. So I'm going to consider just a block diagonal state because, strictly speaking, one cannot create a state with coherence in the energy angle basis out of a thermal state. We need a source of coherence. So here I will not talk about. So this is the local state of our system. And it turns out that the solution can be written in this way by giving the population of each level, of each energy level. So this is how we can write the problem. We want to minimize the work of formation, that is, minimize this function, subject to the local constraints, and the population, of course, should be positive. So it turns out that we have to minimize a linear function subject to linear constraints over a convex set. So this is a linear optimization problem, and it has an efficient algorithm, a complex, that allows to obtain the solutions. I mean, there exists a solution, and there is an efficient algorithm that gives us the solution. So the algorithm would give us the value of work and the state that attains that minimum. But remarkably, we can also find the analytical solution for every number of particles and every state and every Hamiltonian. So let me show you the solution just for dimension 2, because it's really easy. The solution for dimension 2, but we can generalize this for every dimension. So we can state the solution by the following theorem. Given an integral and a block diagonal state, there exists a subset of energy such that the state is written, the population of the optimal state is written in this way. So the form of this state is really simple. If this is, for instance, the population of a thermal state, the solution that we obtain is just like a thermal state. It has a thermal structure, but over the reduced support. There is only a single energy level which has a different weight, but this is like a thermal state with over a reduced support, and one can realize that this is the type of approximation that one does when dealing with large number of particles, that is cutting the tails of the distribution. So again, we can obtain the solution is also the work of formation of this state. that is just obtained as similar to a free energy difference, where this is the partition function of the full thermal state, and this is like the partition function of this quasi-thermal state. This is the normalization constant. Since the solution has a very simple expression, we can also compute the extractable work of this optimal state. And as a corollary, we can obtain also the irreversible work. So let us look at an example. Here we consider, as I said, a two-level system that can be parameterized by just a single parameter here. P beta is the population of the thermal state. And here I'm plotting, here is the work of formation of a single copy, the free energy difference here. And in blue, there is the work of formation of a correlated system over n. That is the work of formation per particle. We can see that we can always get an advantage by using correlations. And here I'm plotting the total correlation per particle. That is, the total correlation is the sum of the local entropies minus the entropy of the global system. And we can see here that all of these states are correlated, and it is interesting that there are some cases where the gap between the work of formation and the free energy is filled by the total correlations. So this is our first result, which is showing that it is cheaper to create a correlated state than uncorrelated ones in the single-shot regime. So the next question is, do we always obtain an advantage with the correlation of correlations? I mean, is it possible that just by creating the correlation we can reduce this work of formation? Of course, the answer is not. Correlations are costly in the sense that the work of formation of the correlated system is smaller than the work of formation of independent copies. And we can show that there is a bound on the amount of correlations that be developed while reducing the work of formation. And this bound has a nice interpretation, because this is the correlation. If we divide this, is the correlation per copy. So the correlation per copy cannot be greater than this bound, and this is interpreted as the dissipated work in the formation process, because this is the work of formation in the single-shot regime minus the free energy difference. So let us now look at the work of extractable work of the optimal states. So in red, I'm writing the extractable work of these optimal states. And we can see that, of course, it is always smaller than, this is always per copy. And this is always smaller than the work of formation. But there are some cases where the work of formation and the work of extractable work are equal. And this we call reversible states, because the work that we need to invest in order to create the state is the same work that one can extract from the reversible transformation. So let us look at these states. If we consider the irreversible work and we expand it in terms of this parameter S, it turns out that the parameter S of the solution is the source of the irreversibility contribution. And reversible states are such that this parameter is equal to 1. So reversible states are the ones that are local over reduced support, thermal over the reduced support. So as I said, the reversible states are the local state whose optimal multipartite state is reversible. So here is one of each. So we know that we can see that here that we have many of them, and they have some interesting properties that will allow us to obtain some intrinsic result in the thermodynamic limit. Okay, so the first is the following. We have that these states, which are reversible, relates in a simple way work, which is in this case of formation or extractable work, with free energy difference and total correlations. So we can see here, as I said before, that if this is the work of formation and this is the free energy, the total correlations are the energy that fills the gap between these two energies. The other interesting property is that the work of formation of these reversible states also bounds the work of formation of any state. I mean, if this is the work of formation of a given state, which is not reversible, it is bounded by two consecutive reversible states. The third property, the third interesting property is that the extractable work of every state is equal to the extractable or the work of formation of a given reversible one. Because here, for instance, for this state, the work of the extractable work is this one, which is equal to the work of some reversible state. Here, for reversible state, I put WB without sub-index because work of formation and extractable work are the same. And for the last property, let us look at how these results behave as one increases the number of particles. So this is what we have as for n equal for 4 copies. This is what we have for 8 copies, 22, and so on. So what we observe here is that the number of these reversible states increases as one increases the number of copies, and also the irreversible work, which is in this case given by this difference. For instance, for this state, the reversible work per copy is equal to this difference. We can see here that as we increase the number of copies, for instance, for this state, the reversible work also decreases. So the last property is the following. These reversible states are dense. I mean, one can find, for every epsilon, one can find a number of copies that goes as 1 over epsilon, such that for every state, there is an epsilon closed reversible state. And this is an interesting property because it will let us to show that the thermodynamic limit of in this way. So the theorem, the second theorem is that let rho be any local state of the system, which is block diagonal, as I said before. Then if this is the work of formation of these correlated copies, which could be the work of formation or the extractable work, this is the same for either of two values of work. When we take the thermodynamic limit, we recover standard reversible results. So the way in which we can recover standard reversible results is by just considering exact or deterministic work extraction or formation, and but allowing correlations. And the rate of convergence to the free energy is of the order log n over n. So here, what we have is what I said before. As we increase the number of copies, the work of formation per copy goes down, and in the limit of n going of large number of copies, this work converges to the free energy, and also for every state, this transformation could be done almost reversible. So this is what we have in mind. So as I said at the beginning, if we allow some error in the transformation, one can recover the thermodynamic limit by considering just tensor product of copies. Here, if you do not allow some error in the transformation, when you create uncorrelated copies, the work of formation is the same. So as soon as you allow that correlation between the systems, you can reduce the work of formation per copy, and you attain the thermodynamic limit, the usual thermodynamic limit. And the correlations, the total correlations that we need, that are present in the optimal state in the larger limit is of the order log n. And in fact, when you look at the thermodynamic limit, the correlation per copy is order log n over n. So in the thermodynamic limit, you recover standard results with correlations that are vanishing small. That's not zero, but that are vanishing small. So with this, we state the relation between fluctuations and the appearance of correlations in the single shot regime. Some generalizations are in order. We can consider, as I said before, local state of arbitrary dimensions. So these results can be generalized to such a case. So then the solution is very similar. Instead of having just a single energy, which is not in the thermal distribution, we have d minus 1 of such energies, and the solution remains almost the same. And we always get an advantage by considering correlated systems. We can also generalize these results to arbitrary system. That is, one can consider not just the creation of copies, but the creation of states which the local density matrix is not the same. And one can also consider systems with Hamiltonian that are not the same. I mean, this state could be a Hamiltonian that is different from this one, and also the populations would be anything, and we always get an advantage, and we can obtain the analytical solution to the problem. So this turns out to be useful in order to generalize the thermodynamic limit. So here I show you a generalized version of the thermodynamic limit, which is the following. Given an arbitrary distribution, which can be continuous, discrete, or anything, let us consider an IID sample of the distribution. The distribution samples vectors of probability and vectors of energies, which in this case is like a sample local states and Hamiltonians. And if we consider an IID sample of this obtained by this distribution, and one computes the work of formation of this of such a distribution, of course, always considering block diagonal reduced state, then this work of formation becomes a random variable as a function of n. But it turns out that if we compute the work of formation over n, this value converges to the mean energy, and the mean energy is with respect to d, the distribution. And so here is the more general result. In the case of copies, what we have is that this is the density of the distribution d. So in the case of copy, this is just a delta function. So, okay, I think that I went too fast, so I'm getting to the last part of my talk, which is a summary. So, as I showed you, we can use correlations to reduce the work of formation of several copies. This is what I showed you in the second part. I showed you also some examples where correlation with catalysis can allow us to perform some interesting tasks, and in fact to obtain a single-shot interpretation of the free energy, I showed you that correlations can reduce the work cost in the creation of multipartite state with local constraints, but they are costly if they are above a given bound. I also showed you that reversibility appears naturally in this framework when the work of formation is studied, reversibility in the sense that the work that one should invest in order to create this multipartite state is the same that the work that one can deterministically extract from them. And at the end, I show you that one can recover the standard thermodynamic results by considering correlated system with correlation that are vanishing small. So other question that we have is that how can we extend this idea to state with coherence? We think that this is possible because while it is not possible to create a diagonal state, a state with coherence out of thermal operations, we need some source of coherence. But it is known that when we act collectively over a coherent state, the amount of resource can be reduced. So there is an advantage of creating a correlated state with coherence when one acts collectively, and this plus what we show when you apply, when we consider the creation of correlated system, we think that this could be also generalized to this case. So this work was done with two students in Buenos Aires, with Facundo Sapienza, which is undergraduate student, and Federico Cerizola, which is PhD students. And if you are interested in the work, you can find in the archive. And let me finish with a small announcement. We are organizing a winter school in Buenos Aires for July. It is called Quantum Simulations, Quantum Metrology with Cold Trap Ions, and it will be 10 days, almost 10 days. You can see that while the title is mainly for cold trap ions, the invited professor will cover many interesting topics from quantum thermodynamics, quantum information, quantum simulation. So Latin American students are especially invited for this conference because we can offer some financial support for them, and the registration is open till the end of April. So I think that I end up early, so this is the end. Thank you for listening.
Thank you for talking. Questions? We have plenty of time for questions.
So when you were saying the correlations, have you checked what type of correlations are appearing? Like, or have you an analysis for just quantum correlations?
Total correlations. We are considering just total correlations.
Have you tried to see, okay, what are more typical correlations that are appearing, like classical or not, or something?